You remember yesterday. You don't remember tomorrow. That sounds obvious. But here's the strange part. The laws of physics don't care about yesterday or tomorrow. Every equation that describes how the universe works, gravity, electromagnetism, quantum mechanics, all of them work exactly the same whether time runs forward or backward. If you filmed the universe at the atomic level and played the recording in reverse, the physics would still make perfect sense. And yet, you age. Eggs break but don't unbreak. Ice melts but rooms full of water vapor don't spontaneously freeze into ice cubes. Time has a direction, and physics, the fundamental rules of reality, doesn't explain why. So today, we're going to talk about one of the deepest mysteries in all of science, why time only moves in one direction. By the end of this lecture, you'll understand what time actually is, why the universe seems to have an arrow pointing from past to future, and why that arrow is connected to something called entropy, a concept that governs everything from melting ice to the eventual fate of the universe itself. My name is Dr. James Mitchell, and this is Science Explained Properly. Let's begin. Before we talk about why time moves forward, we need to understand what time actually is. And I'll be honest with you, time is one of the hardest concepts in physics to define. Not because we don't understand it, but because it's so fundamental that almost every definition ends up being circular. Here's what we know. Time is a dimension, like length, width, and height. You exist in 4 dimensions, 3 of space. You can move left, right, forward, back, up, down. And 1 of time. You move from past to future. But there's something strange about the time dimension. You can't move backward in it. You can walk backward in space, turn around, retrace your steps, return to where you started. But you can't return to yesterday. You can't rewind. You can only move forward. Why? That's the question. And to answer it, we need to talk about something called the arrow of time. Now, before we go further, let me ask you something. If I showed you a video of a glass falling off a table and shattering on the floor, you'd immediately know which direction time was moving, right? Forward. But if I showed you a video of planets orbiting a star, or atoms vibrating in a crystal, or electrons moving around a nucleus, could you tell which way time was flowing? Probably not, because at the fundamental level, physics is time symmetric. The equations work the same in both directions. So the arrow of time, the thing that makes the future different from the past, doesn't come from the fundamental laws. It comes from something else. It comes from entropy. Entropy is one of those words that gets thrown around a lot, usually to mean something like chaos or disorder. And that's not entirely wrong, but it's also not quite right. Now, I'm going to use the word entropy quite a bit throughout this lecture, so let me give you a clear way to think about it from the start. Entropy is a measure of how many ways something can be arranged. That's it. Not chaos, not messiness. Just how many possible arrangements exist. The more ways something can be arranged and still look the same, the higher the entropy. Let me give you an example. Imagine you have a deck of 52 playing cards. If I hand you a perfectly sorted deck, all the hearts together, all the spades together, arranged from ace to king, there's only one way to arrange the cards so they look sorted. But if I shuffle the deck and hand it back to you in a random order, there are billions and billions of ways the cards could be arranged and still look shuffled. That's entropy. The sorted deck has low entropy. Only one arrangement that counts as ordered. The shuffled deck has high entropy. Countless arrangements that all count as random. And here's the key insight. If you keep shuffling, the deck will almost never return to the sorted state. Not because sorting is impossible, but because there are so many more ways to be disordered than ordered. Entropy naturally increases because disordered states are vastly more probable than ordered ones. Let's apply this to the universe. When you crack an egg, the yolk and white spread out across the pan. There are trillions of ways for those molecules to be spread out, but there's only one very specific arrangement where all the molecules are neatly contained inside the shell. So when the egg breaks, entropy increases, and it will never spontaneously unbreak. Not because the physics forbids it, but because the probability is so astronomically low that it effectively never happens. That's the arrow of time. Entropy increases, disorder spreads, things fall apart. And that direction, from low entropy to high entropy, is what we experience as the flow of time. So, if the laws of physics are time-symmetric, why can't we just reverse everything and go backward? Here's the uncomfortable answer. We could, in principle. If you could reverse the velocity of every single particle in the universe, flip every motion backward, reverse every trajectory, the universe would run in reverse. Broken eggs would reassemble. Spilled milk would flow back into the glass. You would grow younger. The physics would work perfectly. But here's the problem. To reverse time, you'd have to know the exact position and velocity of every particle in the universe. And you'd have to reverse all of them simultaneously. Not just some, not most. All of them. And that's impossible, not because of technology, but because of entropy itself. Think of it like this. Imagine you're trying to unscramble that egg we spoke about a moment ago. You'd have to track every single protein molecule, every water molecule, every ion, trillions and trillions of them. You'd have to know exactly where each one is and exactly how fast it's moving. Then, you'd have to guide all of them back to their original positions, perfectly synchronized. One mistake, one molecule out of place, and the whole thing fails. That's why time doesn't reverse, not because it can't, but because the probability of it happening by chance is so close to zero that it might as well be impossible. Entropy is a one-way street. Once disorder increases, it almost never decreases on its own. Now here's where things get extremely interesting. If entropy always increases, if the universe is constantly moving from order to disorder, then that raises an obvious question. Where did the order come from in the first place? Because if entropy always increases, then the universe must have started in a state of extremely low entropy. Highly ordered, highly organized. And that's exactly what we see. Just after the Big Bang, the early universe was incredibly smooth, almost perfectly uniform. Matter was spread out evenly. Temperatures were nearly identical everywhere, and there was very little structure. From our perspective, that might not sound ordered, but in terms of entropy, it was, because there were very few ways for matter to be arranged and still look that smooth. As the universe expanded and cooled, gravity took over. Matter began clumping. Stars formed, galaxies formed, structure emerged, and entropy increased. Now here's the deep question that physicists still argue about. Why did the universe start with such low entropy? To be honest, we don't know. It's one of the biggest unsolved problems in cosmology. Some think it's just an initial condition. The universe happened to start that way. Others think there's a deeper explanation we haven't discovered yet. But what we do know is this: the arrow of time. The reason we experience past and future as different exists because the universe started in a low entropy state, and has been increasing in entropy ever since. That's it. That's the whole explanation. Time moves forward because entropy increases. And entropy increases because the universe started ordered and is moving toward disorder. Let's zoom back out and think about what this means. Entropy governs everything, not just broken eggs and melting ice. Everything. Life, for example, living things, are incredibly ordered. Your cells are organized, your DNA is structured, your body maintains a specific temperature and chemistry. All of that is low entropy. And maintaining it requires energy. You eat food, extract energy, and use it to keep your body organized. But in the process, you increase the entropy of your surroundings. You exhale carbon dioxide. You produce heat. You generate waste. You locally decrease entropy by staying alive and organized, but you increase the total entropy of the universe. That's actually the second law of thermodynamics. Entropy always increases in a closed system. You can create order in one place, but only by creating more disorder somewhere else. Stars do the same thing. A star is a highly ordered object. A dense ball of matter undergoing fusion, radiating energy in a very structured way. But in the process, it's converting mass into energy, spreading heat and light across space, increasing the total entropy of the universe. Eventually, the star's fuel runs out. It dies, its matter spreads out. Entropy increases. Everything that exists, stars, planets, life, galaxies, exists in the process of entropy increasing. We're all temporary pockets of order in a universe that's slowly dissolving into disorder. Here's another strange consequence of entropy. Memory only works in one direction. You remember yesterday. You don't remember tomorrow. And that's not just a limitation of your brain. It's a consequence of entropy. Here's why. Memory requires recording information. To remember something, your brain has to create a physical record. A pattern of neurons, a chemical trace, a change in structure. That's a local decrease in entropy. But to create that record, you have to increase entropy somewhere else. Your brain uses energy. It generates heat. It increases disorder in your surroundings. And that process only works in the direction of increasing entropy. If entropy were decreasing, if time were running backward, the records in your brain would dissolve. You wouldn't remember the future. You'd lose memory of the past. The arrow of time and the direction of memory are the same thing. Both are consequences of entropy increasing. Think of it like footprints in sand. You walk forward and you leave footprints behind you. Those prints are a record. They tell you where you've been, but you don't leave footprints in front of you. You don't have a record of where you haven't been yet. Memory works the same way. The past leaves traces. The future doesn't. Because entropy increases in one direction and memory follows that direction. Now, let's talk about the long-term consequences. If entropy always increases, what happens eventually? The universe reaches maximum entropy. This is sometimes called heat death. It's the state where everything is as disordered as it can possibly be. No more stars, no more galaxies, no more structure. Just a vast, cold, uniform sea of particles spread out across an ever-expanding universe, with no energy left to do anything. No more change. And if there's no more change, there's no more time. At least not in any meaningful sense. Because time, as we experience it, is the progression from one state to another. When entropy is maximized, nothing changes anymore. The universe doesn't end, it just stops. Now that sounds bleak, and it is in a way. But it's also trillions upon trillions of years in the future, far beyond the lifespan of any star. far beyond the existence of galaxies. For now, the universe is young. Entropy is still low enough that stars can shine, planets can form, and life can exist. We live in the brief, beautiful window between the Big Bang and heat death, a window where structure is possible, where complexity can emerge, where the universe can notice itself. All right, that brings us to the end of today's lecture. We started with a simple question. Why does time only move in one direction? And what we've found is that time's arrow is a consequence of entropy. The universe started in a low entropy state, highly ordered, and it's been moving toward higher entropy ever since. That's why eggs break but don't unbreak. Why ice melts but doesn't spontaneously freeze. Why we remember the past but not the future. Entropy always increases, and that increase is what we experience as the flow of time. But here's the part I want you to sit with for a moment. Every moment you experience, every memory you form, every breath you take, every thought you have, is possible because the universe is still far from maximum entropy. You exist in the middle of a cosmic process, not at the beginning, where everything was smooth and simple, not at the end, where everything is uniform and still, but here, in the brief window where stars shine, where planets form, where complexity is possible. You are a temporary structure, a pattern of atoms held together by forces, existing in the flow from order to disorder. And in that flow, you are aware, you notice, you wonder. You are the universe in this particular configuration, experiencing the arrow of time from the inside. Every second that passes, entropy increases. The universe becomes slightly more disordered. And yet, in that process, you exist. Not despite entropy, because of it. Because time moves forward, you can grow, learn, change, remember. Because entropy increases, life is possible. Because the universe started ordered and is moving toward disorder, there is a now, a past, and a future. And you are here in this moment, aware of all of it. That's not an accident, that's physics. In the next lecture, we'll talk about gravity, not as a force, but as something far stranger. We'll explore how mass bends space-time, why falling and floating are the same thing, and why Einstein's insight changed everything we thought we knew about the universe. But for now, take a moment. Feel the passage of time. Notice that you're moving forward, always forward, carried by the current of increasing entropy. And remember, you are not separate from that current. You are part of it. Thank you for listening. I'll see you in the next lecture.